Welcome to Chapter 7 of Geology for the Keweenaw Bay Ojibwe Community College. Today we'll be talking about rocks and minerals. The contents of the presentation are as follows. We'll talk about earth scientists and how they're kind of nature's detectives. We'll get a bit into chemistry. We're not going to get too far. Elements, atoms, your basic building blocks of nature. Then we'll go over in order minerals, igneous, sedimentary, and metamorphic materials. And then we'll end with a discussion of the rock cycle and a little touching upon mineral resources. So, as scientists, right? We are the people that understand nature and can decipher clues from it. For example, we have a picture here from Mars. Are the rocks on Mars the same as the rocks on Earth? What is alike and what is dissimilar between the two rocks? Geologists study rocks for many reasons. One, they do it to find mineral resources, right? The economy, the modern society is more or less built upon the ability for natural resources to be extracted. In that same vein, fossil fuels, oil, gas, coal, what have you. You can geologists also study the natural earth to assess risk from natural hazards such as volcanic eruptions, tsunamis, what have you. Those things are very dangerous. The more we know, the more we can avoid loss of property and loss of life. Of course, the basic science of learning how the earth functions, plate tectonics, volcanism, things along those lines. And you can also use your study of nature to delve into the history and the origin of not only our planet, but the surrounding planets. So let's take bricks as an analogy for rock formation. So when you have brick making, that process involves the physical disintegration of raw materials. You start something, you change it chemically, and you change it thermally. So when you make a brick, you kind of follow the same formation as a rock because, well, bricks are kind of rocks, right? Bricks are made from raw materials such as shale or fire clay, which is not a type of rock, but a name for a rock found on the Earth's surface. Variations of the composition of the raw material, of course, will make different bricks. You've seen gray bricks, white bricks, red bricks, blue bricks, right? For example, the redder the brick, the more iron content is in the original source material. So you take raw material, crush it up into small pieces in a crusher, grind it into even smaller pieces on a grinding wheel, such that you can screen the material and get basically small uniform sugar or flour-sized particles, which you then mix together. When you mix these small particles together, they create a slurry that you pour into a brick-shaped fold. And when the slurry dries, you have a brick piece that is created, but you still have a wet, muddy looking brick. So you have to cook it and let it dry to remove the saturated water, turn it from a mud into a soft material, and then you fire bricks at very high temperatures to turn them into the hard materials that we use for building. This entire process of original material that is processed, formed, and heated, formation of bricks, is a very similar process as we'll see the formation of all the rocks on the planet. Here we have the crushing that we talked about. The fine particles on the grate are going to be ground. The long mud-like mixture that bricks initially form as. And then finally, the finishing product, getting the hard building material that we associate with bricks. So, what are rocks made of? How are bricks a good analogy to rocks? Well, rocks are made up of minerals. A rock is what is known as an assemblage of minerals. Any rock you pick up is, in fact, a composite, a soup, if you will, of many different parts. There's about 20 or so very common minerals that make up the vast majority of rocks. And then there's the rest of the minerals out there play small subsections to give us the diversity. Granite is a good example. We've all heard of granite cabinets, right? A granite is defined as being made of feldspar, quartz, mica, and amphibole. You get those four things, you got a granite. Everything else that's involved to a minor amount alters the type of granite you have, but those four give you a granite. There's other components to definition of granite, but in general, mix those four together, you get yourself a granite. And it looks like that, right? You see white/cream color material with little black dots. But those four, feldspars, quartzes, micas, amphiboles, make up that combination because those black specks, upon closer examination, are different minerals. And those white specks, upon closer examination, are in fact two different minerals. So what is a mineral? Well, a mineral is made up of elements. Everything is made up of elements, correct? We have 8 or so common elements that compose 98% of the continental crust rocks. It's a vast, super vast majority of all the rocks you deal with are just 8 different elements combined in different ways. Some minerals, such as quartz, is composed of just 2 elements, silicon and oxygen. Other minerals, such as amphibole, are more complicated strings of elements. Some elements, of course, occur more frequently than others. And the most common minerals in granite are quartz, feldspar, mica, and amphibole. Again, here you have quartz and amphibole here as examples of somewhat simple and somewhat complicated elemental chains. And there's your big 8. Oxygen, by far the most abundant element in the crust. Silicon comes up next when we get to silicates. You're going to see why that's important. Aluminum, iron, calcium, those are heavy metals, right? Sodium as well. I guess these are all metals. Potassium, manganese. Those 8 right there comprise, as I said, the vast majority of rocks on the continent. On the crust at the top of the earth. And those elements are not just in rocks. They are, of course, in everything. Oxygen is what we breathe, right? Sodium, you put that's salt, right? Calcium's in your milk, etc., etc. So these elements create not just rocks, not just geology, but kind of everything. All right, so let's dive into some basic chemistry, just give you a little background. I'm not going to get any deeper into what you talked about in, say, high school chemistry class, but it's good to have a little refresher here. So atoms. Atoms are the smallest particle that retains characteristics of its said element. Meaning, if you have an atom of oxygen, it's still oxygen. If you break it down into something smaller than an atom, it stops being considered oxygen. That's essentially how that works. Atoms consist of a nucleus, which has protons and neutrons in it, and then an electron cloud surrounding it, as said here. Noteworthy here, we're not using the Bohr model of electrons. That orbit style looks like the nucleus is like a planet and the electrons like a moon. That's not correct with how atoms actually look. So we're not using that for this example here. But we do use the Bohr model to explain the different rungs that electrons can sit on. As you can see here, that example of helium with two protons, and 2 neutrons has a surrounding ring of electrons. Those are, forgetting the words here, I apologize, but essentially they're energy levels that the electron sits at. And then if we look over to neon, which has 10 electrons, that has 2 energy levels at it. So I'm not going to go into the physics and the chemistry of this whole situation, but the way atoms form and the way atoms exist allows them to interact with each other to create the variety we have on the planet here. So important aspects of physical chemistry of how atoms exist. First number that's important you need to know is the atomic number. The atomic number is the number of protons in the nucleus. Each element is differentiated by its atomic number. Each element is different based on the number of protons it has. Neon and helium are different elements because they have different amounts of protons. Helium has 2, neon has 10. Neon and helium are not the same thing, right? You can have a element with a set number of protons, but you can also change the electron count because in these examples here, the protons, neutron, electron count were all the same. Helium has 2 protons, 2 neutrons, 2 electrons. Neon has 10 protons, 10 neutrons, 10 electrons. But if we change the electron count, we create what's called an ion of the material. Here we have 2 examples of this. Oxygen has an atomic number of 8, so it has 8 protons. Oxygen commonly also has 8 neutrons and 8 electrons. But if you have a situation where 2 of those electrons are missing, as shown those vacant spots there, then you have an ion of oxygen, which has 2 less electrons in it. Again, here, silicon on the side there is missing 4 of its electrons. These are creating ions, is what they're called. The ion part is important because, as we said before with quartz is consisting of silicon and oxygen, and they are bonded together. They hang out with each other to create quartz crystals. Oxygen and silicon by themselves are not quartz. Mix them together and you have quartz. This, how they bond together, how they form together, is what we're talking about here, chemical bonding, either ionic or covalent bonding. Ionic bonding, it uses the example here of rock salt, is what happens if you have ions where, for example, this oxygen here is missing 2 electrons. So if you have a different atom of a different element that has 2 extra electrons, they can bond together and the oxygen will grab the electrons from the other element to share. In this example here, no pictures, sadly. Oh, wait, I kind of have pictures. Let's see here. Okay, those pictures kind of sucked. So this example here, we can have sodium that can be an ion of sodium that has an extra electron. And then you could have, sodium is missing an electron. You can have chlorine here that has an extra electron. Those two come together, share what they're talking about. So here you have an example of a sodium atom. The inner energy is filled with energy levels filled with 2 electrons. The outer energy level is filled with 8 electrons. That makes 10 total electrons. But sodium has 11 protons. Sodium has a atomic number of 11, but 10 electrons. That means it's missing an electron. It wants to be balanced, but it's not because it's missing its electron. So you come over here to chlorine. Chlorine has 17 protons, making an atomic number 17, but this particular atom of chlorine has 18 electrons. You see the bottom one there, the capture electron, as it says there? Chlorine has too many electrons. So the sodium and the chlorine will see this electron discrepancy between them and will come together and essentially share that electron, so that the sodium, the Na particle, which had a positive charge, will get the extra negative charge off the chlorine, and they both then achieve that neutral status that they want. Again, I am really glossing over this stuff. If you have questions, leave them below or check out the books. I mean, email, something like that. I'm really quickly glossing over all this material because we got a lot to get through. Like I said, I'm not going to go deep into this stuff. Covalent bonds are a similar approach about the sharing of the electrons, as I said before. And these two different bonding types interact with each other to create the variety that we have. As it said here, water is a covalent bond type of electron sharing as opposed to ionic bonds. So how is all that useful? All that is useful because it allows us to understand the variety of geology from the somewhat lack of variety of atomic organization. And a good example of this is silicon and oxygen. Silicon and oxygen can form together to create what's known as a silica tetrahedron. The chemical formula for that is SiO4. So for every 1 silicon atom, you have 4 oxygen atoms. Now that's cool because the silica tetrahedrons form in physical space something like what you're looking at here, essentially a little pyramid of oxygen atoms surrounding a silicon atom. Or as I should say, oxygen ions surrounding a silicon ion, because they have charges to them because they are either too many or too few electrons. In this example, the silicon atom is missing 4 electrons, and each oxygen atom has 2 additional electrons. That's the pyramid that I talked about before. So this is cool. Do I not? Okay, there it is. Cool. This is cool. I'm going to jump ahead a little bit here because those pyramids can form together in different ways to create a vast variety of different geologic features. We're going to talk about silicate minerals here. Silicate minerals are built more or less off of a base groundwork of this triangle here. And when you bond them, say you leave them individual isolated pyramids, not necessarily connecting them in any way, you have a mineral called olivine. But if you create a chain of them, like that second rung there, you get a completely different mineral. You get the pyroxene group. And then keep going down, make a double chain, you get the amphibole group. Make big, long sheets of chains, you get the micas and the clays. And go all the way down to complicated frameworks, you get your quartzes. We talk about in class micas, for example. Micas are very interesting minerals because they're sort of paper-like and they're transparent. They're super thin. And they are made of the same material as, say, a quartz crystal, which is very hard, has a very distinctive six-sided hexagonal shape. But they're made of the same pieces. It's just the organization of those pieces causes the vast difference that we see, and also causes different chemical reactions. And this is kind of rehashing what I just said. So like a tetrahedron combines together in different patterns to create different minerals. So you can have simple structures like olivines and amphiboles, or complicated structures like quartzes and feldspars. As said in every other time, I'm not going to go with the concept test, but if you'd like to pause and take a look at it, you go right ahead and do that. Cool. Let's talk minerals. Minerals, again, are the ingredients, if you will, of rocks. To get a rock, you need to take a bunch of minerals and mix them together in a certain fashion. A very common, very well-known mineral, we've all seen it, is quartz. Quartz is very distinctive, has a distinctive chemical composition and distinctive way it grows. Minerals, we're going to define minerals as naturally occurring inorganic solids of one or more elements that have a definitive chemical composition and an orderly internal arrangement of atoms. Each of those is important. A mineral is something that's naturally occurring. Plastic is not a mineral because plastic is not naturally occurring. Minerals are inorganic. Humans are not minerals. Minerals have definitive chemical compositions. Every piece of mineral that you pick up that is, for example, quartz, every piece of quartz you pick up is going to have the exact same chemistry. That's how we define it as a mineral. An orderly internal arrangement of atoms is what separates a mineral from a rock. If you take two different chunks of granite and you look at them, they're going to be different amounts of the parts in them. The granite is not defined by the amount of atoms or the arrangement of the atoms. It's defined by the amount and arrangement of minerals. Minerals are defined by the amount and arrangement of atoms. Again, going back to this slide here, each of those rungs on that ladder is the same building block, the silica tetrahedron, organized in different ways to create vastly different minerals. There you have on the left of that muscovite mica. That is second from the bottom, the mica group, the sheets, silica sheets. And if you look at that very closely, that's got a penny there because those sheets lift up like pieces of paper and they're about the thickness of that penny. And that mica is the same atomic material as this quartz. And they're both the same atomic material as that orthoclase feldspar, which again has very different properties, but it's all silica tetrahedrons because all silicates. Then we can go on to other examples like galena and pyrite. Galena and pyrite are they're not silica tetrahedrons. Galena and pyrite have very similar mineral crystal structures, cubes, as you can see here, but they're very different minerals. And then halite, continuing this trend, halite is cubical in the way galena and pyrite is, but halite as well, different chemical composition. That being said, they all are definitive. Every piece of galena you pick up is going to have the same chemistry, and every piece of halite you pick up is going to have the same chemistry as all of its other brothers and sisters. So I've said the word crystal a lot. Let's get into that a bit more. A crystal is an arrangement of the faces of a crystal. The arrangement of the faces of a crystal to form a particular shape is its crystal form. It's what it looks like. We say pyrite and galena are cubic because they form cubes, right? Muscovite mica is sheet-like. Quartz is hexagonal. Orthoclase feldspar doesn't have a crystal. Common crystal shapes include prisms, pyramids, needles, cubes, and sheets. We talked about cubes, sheets, and prisms already. Here is a pyramid shape of calcite. Calcite we can define as having a very particular crystal structure. You can tell this is calcite and this is quartz in part by the shape of the crystals. Quartz crystals have more sides to them than calcite does. Here's needle examples of tourmaline. Tourmaline is actually a gem mineral as well, but it forms very long, straight strands. It does not form shapes like pyramids or prisms. It forms quite literally needles, so we call them needles. Other examples of mineral characteristics include hardness. Now, hardness is not inability to break. Hardness is inability to be scratched. The harder material is, the less likely it is that something will scratch it. If you have something that's harder than iron, an iron nail won't scratch it, for example. The nail itself will give instead of the side of the rock. If you have something softer than your fingernail, you scratch the material will be taken away by your nail. Your nail will not be damaged. So if you try to scratch something with your nail that's harder than your nail, like again, an iron, piece of iron, your nail is the thing that's going to bend back and be damaged. The hardness scale goes from 1 to 10, 1 being talcum powder, if you will, and 10 being diamond, notoriously the hardest thing on the planet. The scale of 1 to 10 is logarithmic, so every step up the scale is an order of magnitude increase in hardness. So corundum is 9 and diamond is 10, but they're not close to each other in hardness. That's why we have the absolute hardness scale on the side. Minerals can have color characteristics, but this one is tricky because not all minerals have distinctive colors. Some minerals, such as olivine, amphibole, pyroxene, biotite mica, are always dark. And some minerals, such as plagioclase feldspar, muscovite mica, things like that, are always light colored. But I'm going to disagree with the slide here. Quartz and calcite can be light or dark depending on what type of quartz or calcite you have. A piece of smoky quartz is black. Cleavage is the word we use to describe how minerals break according to their atomic structure. There's a huge variety of this, as you can see shown here. Here's some pictures of it. Breaking along a plane is an example of muscovite, either biotite or, mica, either muscovite or biotite. Again, to go back to the image here, you can pick each of those sheets of rock up like a piece of paper. It's like a stack of paper laying there, except each sheet is made up of rock. Again, these cubes, if they break along those lines. So you have, two-directional intersect at 90 degrees gives you the shapes. B here is an example of something that breaks along these edges. It can get very, very complicated in the way the minerals break. But again, the important part is this is all defined by the structure of the atoms. To go way back to that slide again, this mica group, your mica's like, again, this piece here, B over here, it breaks into sheets because the atoms are organized into sheets. And it's a lot easier to break them when they're not connected to each other as strongly. Right? It's a lot easier to pick up a piece of paper than it is to rip it in half. All right. Here again is a concept test. Feel free to pause if you want to do it. I'm continuing. Other important characteristics, and each of these are listed in other because not all minerals have these characteristics, and sometimes they're a bit harder to test. Streak is an example of that. Streak is what a mineral looks like when it's powderized. The classic example of this is pyrite on the right here, letter E. That looks gold, right? Pyrite's actually fool's gold. That looks gold, but if you powderize it, if you rub it on, say, a piece of ceramic tile, pyrite as a powder is brownish black. It does not have a gold hue to it at all. What else do we have here? Luster, how light reflects something. If something sparkles, if something reflects a lot of light, it has a luster to it. If a mineral does not reflect light well, such as that orthoclase feldspar there, that's not shiny. So it does not have a shiny luster. Let's see here. Reaction to acid. That's another good one. Some things bubble under hydrochloric acid. Calcite is a good example of that. If you take a little bit of hydrochloric acid, you put on calcite, it bubbles up and evaporates. Not everything does that. Oh, there's a couple of your examples. Oh, another good example of the bottom there is that reacting to hydrochloric acid, like I said. The top there is graphite. Graphite has a streak to it, right? Your pencil is made of graphite. And then fitting everything together here, as it said, that's a piece of granite at the top there. You zoom in on the granite, you notice all the different types of minerals, quartzes, biotites, feldspars, what have you. Those you can break down to an atomic level and look at the arrangement of the atoms, determine how they work together and why these minerals have their components. Cool. So that's minerals. Let's move on to rocks. Again, minerals are the ingredients and rocks are what you make with the ingredients, if you will. There are three main types of ways to classify rocks: igneous, sedimentary, metamorphic. In broad terms, igneous rocks come from cooled magma or cooled lava. Sedimentary rocks come from breaking down a pre-existing rock and forming it again into something new via many different processes. And metamorphic rocks, those are formed when you take a pre-existing rock and you apply temperature and pressure to it, not enough to melt it completely, but enough to alter it in some way. All of these conversations are way deeper than the cover in this slideshow. If you have questions or comments, leave them down below, email me, or talk to me in class. So let's talk igneous rocks. The first type of igneous rock I'm going to talk about is called a volcanic rock. The name should give it away. Volcanic rocks are produced when volcanoes erupt. Notably here, the sentence magma rises to the Earth's surface. If a volcano erupts and the lava extrudes and lays down the Earth's surface, a volcanic rock will form from that. The orange part over there at the top. That's going to form eventually volcanic rocks. Plutonic rocks, by contrast, form when the magma or the lava has not reached the surface yet. So going back here, you have all this material such as that stock and that cell. You see those there in that dike? Those can form when the lava has yet to leave the material. Why do we make this separation? Well, very simply put, when the rock is outside of the Earth, it's on the surface, it cools very rapidly because the temperature is very cold in relation to inside the Earth. If the material does not leave the Earth and stays down below hundreds of feet, it's very warm down there, so it cools a lot slower. Therefore, you get different types of rocks based on how fast they cool. This type of rock difference, the hot cooling versus slow cooling, gives us what we call different textures. Rapidly cooling material produces very, very small crystals. You cannot really see the texture of a rapidly cooled material. You can see the texture on a slowly cooled material, something that cooled below the Earth's surface as opposed to above. The plutonic rocks have large crystals due to slowly cooled, and the rapidly cooled rocks have small crystals. Best way to exemplify this, of course, is with pictures. Notice the granite there. The granite has very distinct whites and blacks to it, right? If you go down to the bottom, that rhyolite, that is essentially uniform in color. You can't really tell where the individual crystals are. Sure, there's little dots on there, but that's the vast majority of that rhyolite. It's a bad example of rhyolite for that. The vast majority of that rhyolite is uniform in color when compared to the granite. Another good example is go over here to the right, talk basalt and gabbro. Basalt and gabbro are essentially the same material, but one cools super fast and gives you essentially a flat black finish like the basalt, and the other one, the gabbro, cools super slowly. So if you actually pick up a piece of gabbro, you can see crystals sometimes the size of your fingernails, and you don't see crystals with basalts. Again, I can also point to the diorite, which is very obviously speckled throughout, or the andesite at the bottom, which is not nearly as speckled. So that is texture in regards to igneous rocks, but there's other ways we can differentiate igneous rocks besides just how big the crystals are. Magma type being the obvious example. Not all magmas are composed of the same material. You can have basaltic magmas, which are low viscosity, meaning they move very quickly, and they have low silica counts. And again, go back to silica. That is, going back here, this dude, silica tetrahedron. The amount of representative silicon and oxygen in the magma dictates a lot about the type of magma that is formed. So if the rock that you melted did not have a lot of silica tetrahedrons in it, because remember, silicon and oxygen are the two most common minerals in the crust. If the rock that you melted did not have a lot of silica in it, then you get a basaltic type material, which is very low viscosity, very fast moving, and creates basalts, for example, right? If you have a high silica content of your melt, of your magma, your lava, you get a more viscous material, more slowly moving, and you can get things such as granites. Basalt and granite are the two phrases we give to these materials, but a basaltic lava flow isn't necessarily going to make basalt. There's a lot more of the conversation, of course. So I've said this a couple of times in this class. I'm not gonna hop on diagrams and stuff like that because this stuff can get kind of complicated. But what's going on in this picture is it's relating temperature decrease. The top is very hot, the bottom is very cold, with the type of atomic structure that is formed. As you see at the top there, that olivine, that is the one where you don't have the silica tetrahedrons connecting with each other, because olivine only really survives at super hot temperatures. So you get a lot of olivine because if the material cooled, the olivine didn't have a chance to come together to form the complicated arrangements that we have. And as you go down that temperature scale, you notice on the left there, the silica tetrahedrons get more and more complicated, from loose olivine to lines for pyroxene to two-sided lines for amphibole to sheets for biotite, all the way down to complex things such as potassium feldspars and quartzes. We can relate the type of rock you have to the type of minerals involved to the temperature where the rock was formed. Again, that was a super fast blast of igneous rocks. It's very, very complicated, really cool. Comment down below any questions. Ask me. I got rock samples. You can take a look at them, right? We'll probably do that in class. Sedimentary rocks. Sedimentary rocks, I said before, are formed when you take a pre-existing rock and you crush it up on the Earth's surface, more or less, and you do something to it. Examples include plastic, chemical, and biochemical formations of rocks. We'll go into each of those real quick. And sedimentary rocks are the vast, vast, vast majority of the Earth's surface. Here are two different examples. We have, well, they kind of both look like canyons, right? But they are sedimentary material. The rock, as it is now, is not its original life. This rock was originally something else that was beaten up by the processes of the earth, rain, water, gravity, what have you, wind, and recombined to form what we have now. Most common thing to, well, actually, here we go. Fantastic. The process of destroying a material and reforming it is weathering, erosion, and the term lithification. Lithification is the recreation, weathering is the breaking down, erosion is the moving. I'm kind of jumping the gun here. I apologize. Let's get into it. Clastic sedimentary rock. Clastic rocks are the rocks that are formed more or less only by physical properties. As it says here, physical and chemical breakdown of any rock on Earth's surface forms a sediment. Sediment is your dirt, your sand, your mud, all that stuff. The tiny little beat up chunks of whatever you had is sediment. You take that sediment, you move it, you compile it someplace, say at the end of a stream, in a lake bed, push it on the glacier, make a sand dune, what have you. And these are pictures of movement of material. Here we have the Himalayan mountain ranges, be the eroded mountain being transported by riverways down to the Bay of Bengal. Again, you have that delta, that bay down there, with all the sediment is entering the Indian Ocean there. Or wind, that is dust being blown off of the Saharan desert. And you take all this material, you break up its original component, move it, and then it recollects. And when it recollects, it can glue itself together. The most common example of this is a sandstone. We're going to talk about mudstone, shales, and conglomerates as well, but sandstone, I think, is the easiest one to explain. Let me okay. So a sandstone is exactly what's talking about. A on the side there on the left is an example of what looks to me to be a sandstone. A sandstone is sand, tiny little grained sand. And when you take that sand and you get it moist, right, you can kind of create mud, make sandcastles, stuff like that. If you let that moist sand dry out, it'll keep its form, right? That's because when the sediment is wet, it releases what we tend to call cement. It releases, oh, sorry, checking something here. When the sand is wet, it releases a cement that binds itself to the surrounding material. And then as it dries, that cement itself dries, and instead of having loose sand, you end up forming a compacted sandstone. Do this under a little bit of pressure, say buried a little bit by water, or buried by material on top of it, and you can compact it further and further and further to the point to where it's not going to crumble anymore. And you get a rather firm sandstone. Shale and mudstone are this with finer particles. Instead of large grained sand, you have small grained mud, right? A conglomerate is what you have on the right here, where you do that same process with bigger material. If you have pebbles or gravel or something like that, you can create what's called a conglomerate. The different types of clastic material is defined almost exclusively by how big the pieces are. In this example here, clays, or things that are less than, what would that be, 10 100,000ths, less than 150 thousandths of an inch across, give you a mudstone. Essentially, you can't really see the material involved. A sandstone, of course, comes in when you get sand-sized grains. Anything larger than that is a conglomerate. Kind of repeating myself here, right? I do like the grain comparison is rice grains to oranges. That always gets me. I know. I'd like to know who wrote that. Cool. So let's end our topic. Let's end our conversation on classic sediment and classic sedimentary rocks. Transportation is a big part of this. In order to understand what created sedimentary rock, you need to look at the processes that move material. For example, let's go to a fast-flowing river. If you have a fast-flowing river, you can have material of all sizes and shapes being transported down the river, right? Very large rocks will float around in a fast enough moving river because the river's got enough energy. So if we find examples with very large pieces of rocks poorly mixed up with lots of small pieces of rocks, we can conclude this originated in some sort of high energy environment like a fast flowing river, versus something that does not have a lot of motion, does not have a lot of energy, let's say a slow moving creek or lake bed or something like that. You don't find large material and very differently sized material constantly moving in a low energy environment. So if we get lots of very similar small sized material forming our sedimentary rock, such as what we have here on the left, or even something smaller like a shale, that is indicative of something with low energy, such as a lake bed. And that's cool because if you find shale, you know you are standing in a former lake bed. If you find conglomerate, you know you're standing in a former high energy environment. If you find sandstone, you're halfway between those two. Cool. Checkpoint, again, take a look at that. Pause, read it if you want. I'm going to move on. Chemical sedimentary rocks. We talked before was clastic rocks, where it's the water and the drying of the water that causes the material to stick together. Chemical sedimentary rocks use chemical processes in their creation. Talking about the first one here is evaporates. Evaporates happen when something evaporates, right? Pretty straightforward. Here I have a picture of the salt deposits on the floor of an ancient lake in Bonneville, Utah. The Bonneville salt flats, you've probably heard of those, right? This salt was in the salty water of the lake. The lake dried up, the salt evaporated out. That's what evaporation is, right? Giving you a clastic sedimentary rock because evaporation is a chemical process. And here it is talking about evaporates. And again, to remind you, if you see an evaporate for, say, salt, you can make conclusions about what the environment was like before today. Salt, evaporate deposits mean you were once in a saltwater location. Biochemical rocks are kind of similar to chemical, except instead of a purely physical process, just evaporation, you can have a living component to the conversation. Coal, for example. Coal, you've probably seen fossilized coal when you've walked around picking up rocks sometimes, right? Well, those rocks were originally biology, so we call that a biochemical rock. Coal, another fantastic example of this. Coal is the carbon-rich rock that's formed from compacted plant remains. It used to be biology. It died, was buried so deeply that it compacted all the carbon together, and now we have coal on the bottom there. The top one is coquina. Basically like oatmeal almost. If you take a lot of shell fragments, compact them together in the same process, you can get that. Again, key factor here, biochemical has a biology component to it. And of course, chalk. Chalk, such as the White Cliffs of Dover, seen here on the left. These are gigantic, massively tall chalk deposits. And when you zoom in with a microscope, you see if those chalk deposits are actually the crushed together bodies of coccolithophores, ancient organisms that were made up of a lot of calcite. That is basically a gigantic graveyard of plankton, more or less. And we do have coccolithophore blooms, as shown on the right here, active in the ocean. What formed the White Cliffs of Dover is still in existence today. So again, that parallels stuff very nicely for us. The other cool thing about sedimentary rocks, of course, is since they're associated a lot of times with biology, you get a lot of your natural gas and your oil deposits found in these guys, right? Oil and natural gas, of course, are hydrocarbons, meaning carbon. So if you, instead of having just pure plant matter, you have other things being broken down, you can create oil. And there's a lot more into this conversation, right? You have different temperature levels and stuff like that. But oil is essentially a biochemical sedimentary rock. In essence, it's the byproduct of it, right? This is a bit of petroleum engineering. I'm not going to get into it too much, but essentially liquid oil is trapped in rock bodies somehow. And that's actually what we tap as we break into these liquid oil remains, pull out the oil to fuel everything we do today, right? Here's a little bit more about coal. There's different grades of it. Cool. The best way to teach this stuff is to physically touch the rocks, right? If you have a mineral museum or someplace, a rock shop you can go there, look at the material, touch it, figure out what's going on, right? Touch a piece of sandstone, touch a piece of shale. Think about what we're talking about here. That's going to do much better than these pictures at explaining the concept. If we happen to be, if you're watching this and they're actually in class, talk to me about it. Hey, can you pull out a XYZ rock for me to look at so I can understand this better? 100%. Love to do it. Metamorphism is the halfway point between igneous and sedimentary. Sedimentary rocks take a little bit of heat and pressure and they kind of squish stuff together, if you will, right? Igneous rocks completely melt something, turn into magma. Metamorphic rocks happen when you have temperature and pressure and presence of fluids enough to alter the material, but not enough to melt it. Approximately, as it says there, 200 to 1100 degrees Celsius tends to be where you find stuff. So you bury something deep or you put next to a heat source. If you put something next to a heat source, we have contact metamorphism. Essentially, you got volcanoes around there. If you put rocks close to the volcanoes, that heat will change them. Classic example of this is limestone. You take limestone and you leave it next to a magma chamber of a volcano for a couple of 10,000 years, you form marble. And what's really cool about that is you can actually look down to the chemistry, you look down to the physical properties of the minerals and the atoms and see how they've changed. Here, marble above and limestone have similar compositions, but not marble has a typically large grain size. So that bottom part there, that limestone is very spotty and has kind of flakes of pieces everywhere. The top there took all that material, started to weld it together, didn't melt the pieces, didn't separate, but it cooked everything together to form larger pieces. Regional metamorphism is the same song and dance, but over a very large scale. That typically is involved with depth. The deeper you bury something, the more likely you are to just have the residual heat of the earth be what's cooking it, and you can get the effects we're talking about in that way. Here we have an example of foliation. Foliation is a distinctive quality of metamorphic material shown down below there. An example of that is a granite to a gneiss. Granite's at the top, gneiss at the bottom. We talked about granites already, right? If you take all those seemingly random specks of material everywhere and you apply heat and pressure to it, what happens is all those random materials kind of get flattened down and they meet with their buddies and they stick together a bit. So all those black and white dots squish down to form black and white lines. Those lines reflect not only that there's enough heat to meld the material together, but there's also enough pressure in the direction of top and bottom in this example to squish them down. Yeah, that's exactly what I'm saying there. Picture of something, I don't quite know. But yeah, these are all kind of going over the exact same conversation. I think this does the best example of explaining it though. Cool. So those are the three types of rocks. Again, I breeze through so much material here, right? There is so much more to talk about igneous, sedimentary, metamorphic material. Ask questions. It's the best way you're going to learn. Feel free to go watch a good YouTube video to expand your knowledge on this, or I can make, of course, recommendations as well. So rounding out to the end of the presentation, here we're going to talk about the rock cycle. The rock cycle is not actually pictured in the slideshow. Interesting. The rock cycle is what happens, is how the different rocks interact with each other. And by that, I mean, if you have a piece of igneous rock, right, and you weather it and you erode it and you turn it into sediment and the sediment forms something else that is, say, sandstone, you have a line going from igneous to sandstone. And if you take that sandstone and you bury it and heat it up enough that it metamorphizes, you have a line going from sedimentary to quartzite, a metamorphic material. And if you keep burying it and it goes all the way and actually completely melts down, then you can connect metamorphic material back up to igneous. You've created a full loop connecting all three rock types in a very believable manner. But you don't have to go in that loop. You can have a metamorphic material, such as an igneous material, such as a granite, be metamorphized and turn into a gneiss, and then destroy the gneiss via weathering and erosion to get yourself a shale or a sandstone. So now you go igneous to metamorphic to sedimentary, still following the same processes. That's what the rock cycle is. Any rock can become any other rock under the appropriate conditions. I guess sometimes rocks have certain chemical qualities that won't exactly fall in, but I think you get what they're getting at here. There's usually like a circular graph, like the water cycle. I don't know why they didn't do that. All right. Last thing we'll talk about, mineral resources. Mineral resources are the important, tend to be important economic qualities that are found in geology. If you have chemical reactions occurring that move various important to humans elements such as gold or copper around, those golds and coppers can deposit in certain locations, and that deposition of materials is what we mine out. Here we have an example of, it looks like smokers. Yeah, okay. Hot smokers. This is something at the bottom of the ocean floor in, say, the Atlantic Ocean. In the mid-Atlantic ridge system. We talked about that last chapter. We talked about plate tectonics. So these guys are pumping out massive amounts of different chemicals. You can see that black soot come out the center there, more or less constantly. And they're filling the oceans with all the various elements and chemicals that life sustains off of. They are quite literally, like, let's see, for sulfides, circulating seawater, what have you. They are creating the minerals that create the ocean. As said before, these minerals are moved around, transported. Lots of fun stuff happens to them. I don't know what this picture's trying to get at. So, yeah. The classic example, of course, since we're the KBOCC, we're right next to the copper country, right? That's the Keweenaw and Houghton and Calumet and all that jazz. It's called the copper country because it's full of copper. It is full of copper because way back, 100 million some odd years ago, when the mid-Atlantic ridge, the mid-continental rifting system was essentially tearing the United States in half, there was lots of flow of hot water and lots of flow of material throughout there. Some of the water that was flowing around was very rich in copper. As the mid-Atlantic ridge, as the mid-continental rift system, sorry about that, closed up, the copper was deposited in kind of any place it could sit. The Keweenaw, the copper country, happened to get a whole lot of copper deposited in this manner, which we now mine out. A more relevant example possibly to anyone else would be anyone that has a well system at home. If you drink well water out of your house, you know that the water tastes different, right? It has a metallic taste to it because that water has metals in it. And if you have old galvanized piping or something like that in your house, that pipe gets thickened and gets material built up inside of it. You got to replace those pipes pretty often. The metal in your water is the same metal that deposits iron and bauxite and copper and silver and gold all throughout the world. It's the exact same process, just at a geologic time scale and at geologic temperatures. And those are mineral resources. So that's the conversation. This is probably my least favorite chapter to cover of all of these because it glosses over so much material so fast. Most other geology courses you have has, there we go, steps 2, 3, 4, 5, 6, and 7 are all the individual chapters. The Good Earth covers a lot more than geology, which is why we use it for this class. But yeah, this, as I said, 2, 3, 4, 5, 6, and 7, all their own individual chapters of information. That's how big this stuff can be. So if you got questions, definitely please ask, comment down below, shoot me an email, whatever works best for you. Thanks for listening. Have a good day.